Neural response interpretation through the lens of critical pathways. We start with the question, is critical input information encoded in specific sparse pathways within the neural network? And if so, how can we identify such pathways? Previously, the pruning objective is proposed for identifying critical pathways. The pruning objective is defined as selecting a small subset of neurons for which the response remains close to the original response of the network. Intuitively, there are many subsets that can make up the original output. We show that pathways selected by pruning do not necessarily encode critical input information. If you are interested to know how this happens, in our paper we show how, by devising a pathological greedy pruning algorithm that intentionally searches for irrelevant pathways while satisfying the objective. If the pathways which are identified by a pruning objective are not critical pathways, the question again is, do such sparse pathways exist? We thus try another direction. To ensure pathways include critical fragments of the encoded input information, we propose pathway selection by a neuron's contribution to the response. In other words, we propose selecting pathway of critical neurons. In this experiment, we see that pruning objective can result in pathways that contain neurons that were originally dead but are now activated in the selected pathway. In fact, the pathways have diverged from the original sparse representation of the network. We also observe that different solutions for solving the pruning objective result in different pathways which do not overlap. This shows that there exist many pathways that can have the same response as the original network. We also investigate what patterns are associated with the pathways selected by pruning objective and by neuron contribution. In the first row, we search for an image pattern that maximizes the response when the network is restricted to each pathway. We see the image patterns for pruning solutions are meaningless, while for neuron contribution methods, the optimized image represents features of the original image. In the second row, we show the semantic association of the most important neuron in each selected pathway. We observe that for neuron contribution methods, the neuron is unique and related to the bird's eye. However, for pruning methods, we see that the most important neuron is different for each method and is not semantically associated with the bird image. In short, this experiment introduces further evidence that the pathways selected by neuron contribution encode image features, while pathways selected by a pruning do not. Having discussed critical pathways, we now proceed to see if we can identify the features in the input that are associated with the critical pathways. By doing so, we can identify critical input features. We can show that pathways of critical neurons are locally linear around the input. This is not to be confused with ReLU networks degenerating into a linear function at a single point. ReLU network in general is not linear in a neighborhood around the input. As the critical pathway is locally linear, its gradient reflects the local critical input features. As such, we propose a feature attribution method called pathway gradient. In this image, we observe the pathway gradient for critical pathways of different levels of sparsity. As we select sparser critical pathways, pathway gradient reveals input features that are more critical. We compare the pathway gradient method with several feature attribution methods. Pathway gradient generates saliency maps at the same resolution as the image. Below, we also see a feature importance evaluation experiment for different attribution methods. We observe that pathway gradient is indeed identifying critical input features and is not just visually interpretable. This experiment also confirms that selected pathways using neuron contributions are associated with critical input features. To recap, we show that critical input information are encoded in specific sparse pathways within the neural network. We show that pruning objective does not identify critical pathways, and we propose selecting pathway of critical neurons. We use critical pathways to identify critical input features and thus propose a feature attribution method called pathway gradient.